Okay, now for the next portion, what we have to prove, that order of x at x inverse is equals to p to the power m. Okay, so in order to prove this one, we will consider a mapping, and we will name this mapping as phi, and this will be a mapping from h to x at x inverse, and is defined by phi of h is equals to x at x inverse for all h belongs to capital H. So for this mapping, we will prove two things, that this mapping is 1 1, phi is 1 1, 1 to 1, and then we have to prove that phi is on to. So in order to prove that phi is 1 1, we need to take it as h1 and y2, two elements, not y2, we will be taking h1 and h2, two elements which belongs to where, capital H. These are the arbitrary elements, and we know that according to the definition, phi of h1 will be equals to what, x h1 x inverse, and phi of h2 will be equals to x h2 x inverse, right? Now in order to prove phi is 1 1, we will take x of h1 is equals to phi of x h1 is equals to phi of h2. Now we will be substituting the value of phi of x h1 as x h1 x inverse is equals to x h2 x inverse. Now using the left and right cancellation law, okay, left and right cancellation law, we will sort it out, and we will be getting h1 is equals to h2. That means phi is 1 1. Now for phi to be 1 2, let x h x inverse be any element. This is element where in x h x inverse, okay, then an element h belongs to h such that phi of h is equals to x h x inverse. This is according to the definition of onto, which implies that phi is onto. Okay, now since phi is 1 1 and onto also, okay, then we can clearly understand this one, that see, phi has what kind of elements phi has. Okay, see, order of x h x inverse will be equals to order of h, and that will be equals to p to the power m. How you will be getting this one? Okay, this you will be getting it clear. See, phi has an element. What kind of element? X h x inverse. That means it has an element like h in the middle, which already belongs to the group h, and that is also already a p-Sylow subgroup, right? And for this one here, for x h x inverse, this one you can see, this contains the elements which has this element, and x and x inverse form in the combination with x and x inverse. So clearly you can understand this value of h will be continued. Okay, the much will be value of h. That means the much element is there in h. The much will be belonging to, the same will be belonging to x h x inverse, because this is the combination of this kind of elements, right? So if it will be h1 h2, it will continue till when? Till the elements are there in h also. So that means the number of elements which are there in h, the same number of elements will be there in x h x inverse also. So this proves that order of x h x inverse is equals to order of h, and which is equals to p to the power m. So in this way, this theorem is completely proved. Okay, I hope this theorem is now clear to you. Thank you.